try to play with the matrix. And let me, first of all, try to save what we did into a text file. Because for personal reasons, because I would like to update the R file that I made available to you. And also because so it's an opportunity to show you how what we did can be saved and can be more efficiently redone and in this case modified. So let's use the instruction save history. And I think that we just need save history, open those parentheses, and this saves the history in the directory where you started out from in Linux and Mac, and saves the history in the main directory of R, where the executive program sits in Windows. So in my case, it's, let me see, it should be here. Because I don't remember from which directory I started up. Sorry, 1 second, I try to get it. Okay, let me give the full path. Now it should be there. I gave the full path where I wanted the file to be saved. Let me see if it is there. Okay, it's here. Okay, this is my history. And I need to clean it. Let me increase the font. I need to clean it because this saves. So all what I did since the beginning of our lecture, since the beginning of our exercise, I need to clean it because some of these instructions are not needed. So I'm removing all the checks. And also I remove the plots because I don't need them. And these are, I copied the definition of the utility functions, which are not really needed for what I have to do now, but they are needed if I want to start the exercise from scratch. So this is the definition of the array. And this is the definition of the elements of the array. You may remember this is exactly what we did. And then there is the computation of the eigenvector. Okay. Now here I copied this value, so it should be better if I do like this. I assign a variable for the computation of the highest eigenvalue, and then I can write here parenthesis PR31 minus 4 divided by 3, because I want to make the procedure automatic basically. So I can just copy, cut and paste this file in R and everything is redone. Okay? And then here there is consistency, this is fine. Now, let me see. Okay, this is the computation of the overall utilities. Okay, here we are. Perfect. This is extremely useful because now, if I wanted to redo everything, you see, I select the file, I copy, and then I go to R, and let me see if it works. It should work. Yeah, perfect. Let me see, U18, it's, okay, U19. Yes, it works. Okay. So now, basically, this file, I can modify it. So I keep the utilities defined as it was before, and then here I want to work on the matrix. So remember the indicators: economical benefit, fish, landscape, and tourism. Now let's try to give more weight to the economical benefit. Basically, 1, 2 is economical benefit with respect to fishes. Let's put 3. 1, 3 is economical benefit versus the landscape is 5. Let's keep it. Economical benefit with respect to the downstream recreational purposes, let's put 7. This means that I give less weight to the recreational purposes. I give an intermediate weight to the landscape, and I give less weight to the fishes. Okay? Or the opposite, let me think. No. Yes. Just 1 second, because probably it's the opposite. I give less weight to the last one, which means tourism, intermediate weight to the landscape, and more weight to the fishes. Okay? So the fishes are more important than the landscape, and the landscape is more important than the tourism, according to this first classification. Perfect. Now, 2-1 is, at this stage, is 1/3. 2-2 is 1. 2-3 is basically fishes against the landscape. And I said that it should be more important, but not really much more important. Let's use, I don't know, 3. Let's try with 3. Or let me put 4. And then 2-4 is fishes against the tourism. Should be more than 4. Let me put 7. Okay. Now 3-1 is 1/5. Perfect. And 3-2 is 1/4. Because I look at the 2-3, 2-3 is 4, so 3-2 should be 1/4. 3-1. 3-4 is landscape against tourism. It should be something like 3. Let's try. 4-1 is 1/7. 4-2 is 1/7 again. Yes. 4-3 is 1/3. 4-4 is 1. I don't think it's really consistent because 4-1 is tourism against fishes. Shouldn't have the same value than tourism against landscape. This should be 1. This should be 1/5, I think. Or let me think about it. Yeah, should be like that. So if this is 1/5, 1/4 is 5. Not sure, let's see what happens. Okay, and now the rest of the exercise is fine. So now let me do like this. This should compute, should put into R the new matrix, and should allow us to check the consistency. So let's see. And you see that it's not really consistent. It's close to consistency, but there is something wrong, so we should try to change it. 0.1 is a bit above the threshold, and I don't think it's satisfactory. So I made some mistake around, so let's try to go back to the file and make the matrix more consistent. This is what usually happens. In practice, usually, especially if you have many indicators, the result is that the matrix is not consistent. So let's go back. And there is for sure a mistake somewhere. So basically, I said that let's forget about the economical benefit, which is the most important of everything, because you see that with the first 4 evaluation, we basically say that the economical benefit is more important than the other 2 indicators. But what I am establishing here is that the economical, the fishes are more important than landscape and tourism, and they have the same importance. Because I corrected the matrix. So now the result is, but let me put it back at the previous stage. So the fishes are more important than the landscape, and the landscape is more important than the tourism. Okay. So when I turn to the second row is relates to fishes against the economical benefit is 1/3. Fishes against the landscape, it's 4, and fishes against, I think it's here, which is not really consistent. Let me say. You know, this is still consistent. 4 and 7. This is still consistent because it means that the last one is the less important, which is fine. And now let's see, this one is okay, this one is okay. And then this one should be okay. Okay, let me try to put 9 here and 5 here. So in this case, if I put 9 there, which is 2, 4, 4, 2, should be 1, 9. And if I put 3, 4 equal to 5, 4, 3 is 1/5. Okay, let's try it in this way, if it improves the situation. Copy it. Control F. No, it's worse. So, what should we do? So basically, and if you have any suggestion, please tell me. Otherwise, I move forward according to my judgment. So basically, what we changed here is not fine. So let me go back. And if it is not fine, then it means that probably I should put 5 here. 1, 4, 1. It's not consistent. 1, 4 is 7. 4, 1 is okay. This is not correct. And 2, 4 is 7. Okay, let me try again. Let me try again and see what happens. Yeah, now it's much better, thank you. And still I think that probably, in order to improve again, probably we should, let me try if I put 5 here and 2 here. So I change it to 4, I bring it to 5, and 3, 4, I bring it to 2. So 2, 4, it means 4, 2, 1/5, and 3, 4, 1/2. Let me see, I probably, in this way, it becomes even more consistent. So we start from a value of 0.06, 0.03, yeah, it's more consistent now. Probably we could work around even more in order to improve it, but in this case I think it's fairly fine. And let's look at the weights. And you see that indeed it comes forward what we were expecting. much more to the economical benefit, and then decreasing weights while we move through fishes, landscape, and tourism. Okay, perfect.
Can you show again the value of the match?
Yeah. Can you read that? Okay. Okay, and now we can move forward with the computation of the utilities. So I'm copying them in R, and let's see the results. U80 is 0.56, U90 is 0.57, U100 is 0.58, U110. You see that there is a maximum of utility for 100. This is a clear example where you see that in the range of the alternatives you find in the middle of the range the maximum of the utilities. Just 1 second, I look back to the shape of the utility functions. Yeah, you see that there is a nonlinearity in the range that we are considering. If you see the indicator I3, which is the landscape, you have a utility of 1 for a design flow up to 100. And then utility decreases for increasing river flows. This nonlinearity is the reason why we found a maximum of the utility for a design flow of 100. Because when you make the computation up to 100, the utility associated to the indicator I3 is constant and equal to 1. So it doesn't have an effect on your decision. But when you move forward from 100 upwards, you start getting the utility of the indicator I3 decreasing. And this is why we got a maximum of utility for design flow equal to 100. If I put this utility function constant up to 110, I am expecting that I would get a maximum for design flow of 110. Even if the weight that we give to the indicator I3 is reduced, nevertheless we get a maximum of convenience for this indicator, in this case for design flow up to 100. Let's try to make this experiment. And now that we have the text file with the whole exercise, we can play with it. So let's try to modify this utility function for the indicator I3 to check if we indeed, by modifying it, we shift to 110 the optimal design flow. So let me modify this utility function for the indicator I3 by substituting 110 instead of 100. It's very easy. It means that we keep the utility constant up to 110 instead of 100. And let's see if it changes the final result. And no need to change the matrix for the pairwise comparison. We just need to change the utility function. So let me go to the file, and here is the definition of the utility function. Basically, the problem is that we need to change its U3. Okay, so basically we have to put here U3 110 equal to 1, and here we have to make here 1 divided by 40, because 110, the range, the gap between 110 and 150 becomes 40, and here I have to multiply by 10. That's it. So let's see what happens. I just need to copy the whole file. I copy it. There is an alternative to cut and paste, which I mentioned to you, which is using source. That's it. And now we can write, we can see what is the result. U80 is 0.56. U90 is 0.57, U100 is 0.58, U110 is 0.59, and U120 is 0.58. You see that we shifted the optimal solution to 110 by just changing the utility function. And why I basically wanted to make this check? Because when I realized from the previous exercise that there was a maximum in the range of the utility, it means that basically you have utility that in the range that we considered between 80 and 120 increases, and then a certain point decreases. This is a nonlinear behavior. And therefore, if there is a nonlinear behavior in the results, and given that the weights are constant, I understood that there must be a nonlinear behavior in the utility functions in that range. Because otherwise, if the utility functions were linear, which means that the utility is linearly increasing with the river flow, and the weights are kept constant, so we get finally a linear combination of linear functions, the result should be linear. So steadily increasing overall utility for increasing river flow. The fact that we found a nonlinear behavior with a maximum brought me to realize that there must be some nonlinearity. And therefore I went to the utility function to check where the nonlinearity was. And then I went back to the file, as you may remember, and I realized that the first utility function is linear between 30 and 150, so it's linear in my range. The second is linear between 60 and 150, so it's linear in my range. The third is linear between 100 and 150. It's non-linear in my range. And it's the only one, because the other one is linear in my range, because it's zero. Sorry, it's also the last one is non-linear. Yes, also the last one. But the last one is given a weight that is very low. I didn't realize that before, but I'm just now providing the explanation. The last one is giving, we give it a weight that is very low. So it's not as effective as the third one. So I realized that it could suffice to change this utility function to shift the maximum. Basically, what is the take-home message for you? When you apply these mathematic tools, you always have to keep a tight link with the physical process, as I said before. So when you get the result, you have to think about water, about your design flow, about what's happening. And this has two purposes. The first purpose is that if you keep a link with the physical process, you can realize if you made mistakes. Because in this case, you know, I made this check. I gained an interpretation, and the interpretation allowed me to check if the result was fine. I changed the utility function, realized that the result is changing as I was expecting. It means this is a check. Because if I got a different result, then I would say, why is that? So this is the first purpose. The second purpose, the first purpose is very important for an engineer. You have always to care about the risk of making mistakes. You always run the risk of making mistakes. And of course you have to adopt all the possible precautions to avoid these mistakes. You have to be very precautionary. And therefore continuously make check. Draw graphs, look at the order of magnitude in order to make your checks. And the best way to make a check is to keep the physical process in mind and immediately translate the numerical results to the physical process. First reason. Second purpose, if you keep a tight link in the physical process, your discussion with the stakeholders, as I said, becomes much more effective. Because in this case, this check that I performed basically convinced you that my interpretation was correct, that the method works, etc. This is extremely important. Because with the stakeholders, it's extremely important that you convince them that you gain good interpretation, that you know the tools that you are using, and that your perception is fine and the process is transparent. So this is my message. Always keep a tight link with the physical process. We are engineers. Of course, we use mathematics to support our work, our job, our decisions, but always keep a link with the practical issues. And again, the fact that we are giving now, we gave more weight to the economical benefit, and we get the solution that we are expecting, so increasing the design flow, this is always very useful. This is also very useful. If you speak with your stakeholders, just to show, look, see what happens if we adopt your opinion. Then the resulting decision is this one. Now see what happens if, okay. And these checks, of course, should be made in a wise way after formulating the opinion of people. We shouldn't allow people to change the opinion after they have seen the results, of course. In a wise way, we should use these methods, these solutions to make people aware that our experience and perception are fine. Okay, and now, don't forget the graphical representations. We developed just the graph of the utility functions here, but the message is every time that you can prove that any time that you can show graphically the results, it's much better than using numbers. And for this reason, in water resources management now, there is an increasing use of decision support systems which are based on object-oriented programming. Object-oriented means that we don't program through numbers as we did today here, but you program by playing with objects. So for instance, if you want to change from a low design flow to a higher design flow, instead of using a number, 80 to 120, you use pictures of pumps. Small pump, big pump. And then maybe you put the number close to it. But using pictures and in general objects, you can better display the links. So if you have two reservoirs, for instance, you connect them with a line, it's much better to show the two reservoirs connected with a line than just saying you have two reservoirs which are connected. And there is an increasing use of these tools, so keep in mind when you hear about object-oriented programming, this is what it means. And if you use programs like R, because they are more useful for you, don't forget to draw graphs. So in this case, for instance, when they say plot, and then the alternative solutions, C, 80, 90, 100, 110, 120, and then C, the utilities, 180, U80, 90, U10, U110, U120. And then if you just make this plot, of course it doesn't look nice. Sorry, I'm working on the file, so let me go here. Of course this plot doesn't look really nice. Here it is, and then you should put the labels in the axis and also in the axis, and also you may use the red colors to display these dots. And another good thing could be, let me go back to put the utility in the range 0, 1, so we can say y limit equals c 0, 1, which is a bit better, but still 0, 1 maybe no, it's not better, because you don't see really the maximum, it's not a good thing, but still maybe using 0.41 for instance, or the logarithmic scale, I'm not sure if it is better. Still it's probably not really visible. 0.4 or 0.8, yeah, it becomes a bit more visible. So basically drawing plots, it's much better than just showing numbers. For instance, in this case, you see that there is not a big change. And by using this representation, instead of numbers, you see that there is not a big change. So one may say, why care about this? It's really a small difference. Okay. I think I am done. If you have any questions, I will put this file, which I saved, available in the zip file that is related to this exercise. I will put this file available like R-code 2015, something like that. Okay? And it's not commented. Please allow me to put it into available without commenting it, because it's fresh in your mind, so you can put comments. Okay. I am a bit early, but still, if you don't have any questions. If you have any questions, I am available